Alright, hello and welcome to the video. In this video, I'm going to be going over critical points, local extrema, intervals of increase and decrease, and the first derivative test. So let's get into it. So this video is going to be mainly focusing on the first derivative, whereas the next video is going to be on the second derivative. So just as a recap, the first derivative, f prime of x, tells us the slope of a function basically at any point. So it tells us its rate of change. So if f prime of x is positive, we know that means the function is increasing. If f prime of x is negative, we know that has to mean the function is decreasing because it has a negative slope. Now, if the first derivative is 0, basically what that means is that your function is going to flatten out at that point. So usually that's going to be a max or a min. So like that's a max, that's a minimum. At both those points, the first derivative is equal to 0. Basically, your slope at that point is kind of leveled out, and so your function just has a flat spot at that point. Now, the first derivative being equal to 0 doesn't necessarily mean a max or min, which these are called extrema. It can be that your first derivative is 0, but you don't necessarily have a max or min. Like here, with y equals x cubed, your first derivative is equal to 0 at 0 because your first derivative is just 3x squared. But if you notice, it does not reach a maximum or minimum at that point. Alright, so what if the first derivative approaches infinity, either plus or minus infinity? Well, basically, what that means is that you're going to have usually a vertical tangent, so something like that, where at this point where the first derivative approaches plus or minus infinity, your graph is kind of just going to be pointing straight upwards. So this is if it's approaching positive infinity. If f prime is approaching negative infinity, it would be kind of the other way. All right, so let's look at what a critical point is. All right, so the definition of a critical point is a place on a function where the first derivative is either 0 or undefined. So, for example, if you have f of x equals x cubed, like in the previous example where I showed you, the first derivative is just 3x squared, and that has a critical point at x equals 0. So basically, since the first derivative is 0, it's just going to flatten out there. But an example where it's undefined would be if you have f of x equals the cube root of x. That's the same thing as x to the 1/3 power. And if you differentiate that using the power rule, you get 1/3 x to the negative 2/3, which is the same thing as 1 over 3x to the 2/3. Now notice, the denominator is going to be 0 if you plug in x equals 0. So the first derivative is undefined at x equals 0. And if you think about the cube root function, it kind of has that vertical tangent like I was talking about. Now, notice a critical point does not necessarily mean that the function has a maximum or minimum at that point. It just means that the derivative is either 0 or undefined. But every single maximum or minimum does occur at a critical point, because every single maximum or minimum has to occur where the first derivative is 0, because it flattens out at that point. Alright, let's do an example. Alright, so we're given this function, f of x equals the cube root of x times x squared minus 1. And we want to find the exact locations of all the critical points of this function. So recall, we just said the critical points are places where the first derivative is undefined or 0. So to find out those locations, we just need to take the derivative of this function. Now, we have a cube root. I'm going to write that as a 1/3 power. So x to the 1/3 times x squared minus 1. If we multiply this in, that's going to be, we add the powers here. So x to the 1/3. So 1/3 plus 2, that's 6/3 plus 1/3, that's 7/3. So we have x to the 7/3 minus x to the 1/3. Now, this seems right for us to take a derivative because we have it in a form where it's nice to use the power rule. So our derivative is just going to be the derivative of x to the 7/3 minus x to the 1/3. So for the first term, we bring that power down and we reduce it by 1. So 7/3 minus 1 is just 4/3. Minus, for the x to the 1/3, we just bring that 1/3 down. Now we subtract 1 from 1/3, so that's just negative 2/3. So this is 7/3 x to the 4/3 minus 1 over, because we have this negative in the exponent, 3x to the 2/3. Okay. So now, to find the critical points, we need to set this equals 0. Well, we need to find where it's 0, but we also need to find where it's undefined. So, to find where it's 0, we just set the whole thing equal to 0. 7/3 x to the 4/3 minus 1 over 3x to the 2/3 is equal to 0. I can see that we multiply both sides by 3, and that will get rid of that 1/3 in both of their denominators. So we get 7x to the 4/3 minus 1 over x to the 2/3 is equal to 0. Let's add this to both sides. And now, since we have this 1 over x to the 2/3, we have the x to the 2/3 in the denominator. We can multiply both sides by x to the 2/3. Now, x to the 4/3 times x to the 2/3, we just add those exponents together. So that would be x to the 6/3, which is just x squared. So what we'll get is 7x squared is equal to 1. This gives x squared equals 1/7. So x is plus or minus, because we have a squared, the square root of 1/7. And you can simplify this a little bit. You get square root 7 over 7. Okay, so now we need to find where this derivative is undefined. Well, as you can see, in the denominator, we have an x to the 2/3. If we plug in 0 to that, the denominator will just go to 0. So then that would be undefined, meaning that we have a critical point at x equals 0. So we've taken care of all the possibilities. We found where f prime is 0 and where f prime is undefined. So if you look at the graph, these will all be the critical points, but we want to find the exact locations of those. So we have the x values, but to find the y values, we just plug it back into the original function. So let's do that. All right, so first let's just plug in the easy one, x equals 0. So when x equals 0, we get the cube root of 0 times 0 squared minus 1. So this is just 0 times negative 1, which is just 0. So one of our critical points occurs at 0, 0. Another one of our critical points happens where x is the square root of 7 over 7. So if we plug that in, we get the cube root of square root 7 over 7 times square root 7 over 7 squared. That's just 7 over 49, which is 1/7, minus 1. Let's simplify this a little bit. The cube root of a square root, we can distribute this cube root. The cube root of a square root is just a 6th root, because this is the same thing as 7 to the 1/2 over 7 all to the 1/3. and we can multiply these exponents. So this would be the sixth root of 7 over the cube root of 7. And then 1/7 minus 1, that's 1/7 minus 7 over 7. So negative 6 over 7. So this is negative 6, sixth root of 7 over 7 cube root of 7. All right, one more. So for our third critical point, we need to plug in negative square root 7 over 7. So f of negative square root 7 over 7. Again, we're going to have the cube root of that. So cube root of negative square root 7 over 7 times negative square root 7 over 7 whole thing squared. It's just 7 over 49 because the negative goes away. And that's 1 over 7th. Subtract 1. That's negative 6 over 7. And then the cube root of all this, we can distribute that again. We have this negative, but the cube root of negative 1 is just negative 1. So that just gets pulled out. And then we have a sixth root divided by cube root of 7 times negative 6 over 7. These negatives will cancel out. We'll get 6 sixth root of 7 over cube root of 7. Alright, these are all of our critical points. Alright, so as I briefly mentioned before, extrema are basically your maximums and minimums of your function. So local extrema are places where your function reaches basically a local, or within one specific area of the function, it reaches an extreme value. So what I mean by that is, let's say a function that looks like this. So clearly the function goes off to negative infinity on the left end and positive infinity on the right end. But you can see in this little zone right here, it does have a maximum. But because it's not the absolute maximum of the function, it's called a local maximum. Technically, this function has no absolute maximum or minimum because it's just going to keep increasing and keep decreasing on its ends. Now, a function can also have absolute or global extrema. So if you have something like this, this has an absolute maximum right here because that's the highest point of the function. But it's also a local maximum. So they can be both. Every global maximum is also a local maximum because in that area, it's a maximum. But every local maximum does not have to be a global maximum. So the first derivative test is a test that you can use to determine if a critical point is a local maximum or a local minimum, or if it is neither. So assuming that some function f is continuous on some interval containing this critical point c, if the function's derivative switches from positive to negative at x equals c, so if the function switches from increasing to decreasing at x equals c, then the function has a local maximum at that point. On the other hand, if it switches from decreasing, so a negative derivative, to increasing, a positive derivative, at that point, then it has a minimum at that point. But if the derivative does not switch sign to x equals c, then it has neither a maximum or a minimum. So basically what this is saying is for this first one, if it switches from positive to negative, so you're increasing and then you start decreasing at this point c, you can kind of visualize in your head what that looks like, and that makes sense. On the other hand, if it's decreasing and then it's increasing, it had to have reached a minimum point somewhere before it switched. And on the other hand, if f prime fails to switch, so it stays increasing or it stays decreasing, like this, then it makes sense that you're not going to have a maximum or a minimum at that point. All right, let's do some practice with what we've learned. So for this example, we have f of x equals x cubed minus 6x squared plus 9x plus 2. we want to find where the function is increasing and decreasing and find all the maxima slash minimum of the function. So the first step is we need to take a derivative because that's going to tell us where the function is increasing and decreasing. This is just a simple power rule. The derivative of x cubed is just 3x squared by the power rule minus 6x squared. We multiply that 6 and 2, so minus 12x. And then the derivative of 9x is just 9. And the derivative of plus 2 is just a constant, so it's 0. Okay, so now we need to find the zeros of this, because the zeros of this function, it's going to basically act as the boundary between where the first derivative is positive and negative. So if we set this equal to 0, we can factor out 3 from all these terms. So 3x squared minus 4x plus 3. So 3 times x squared minus 4x plus 3. And then we can factor this even further because we need to know what multiplies to 3 and adds to negative 4. That's just negative 1 and negative 3, because negative 1 plus negative 3 is negative 4. Negative 1 times negative 3 is just 3. So this factors like x minus 1 times x minus 3 with that times 3 out in front. And so our zeros of our derivative are just going to be x equals 1 and x equals 3. So a helpful tip for these kinds of problems is to draw a number line and then to label or kind of mark where your zeros of your first derivative are. So for us, we have x equals 1, x equals 3. And then the next step would be to plug in points between those zeros, those critical points of the first derivative. So if we plug in a point between x equals 1 and x equals 3, let's try x equals 2. You plug it into the first derivative instead of the function because you're trying to find out the sign of the derivative to see if it's increasing or decreasing. So f prime of 2 is just 3 times 2 squared minus 12 times 2 plus 9. That first term is just 3 times 4, so 12 minus 24 plus 9. So negative 12 plus 9. So this is negative 3. And because our first derivative is negative between x equals 1 and x equals 3, that means our function is going to be decreasing between x equals 1 and x equals 3. So now let's plug in a test point below x equals 1. Let's try 0. So f prime of 0, that's 3 times 0 squared minus 12 times 0 plus 9. Both these terms are just going to be 0, so we just get 9, which is positive, meaning that our first derivative is positive for x values less than 1. Finally, if we plug in an x value greater than 3, so let's try x equals 4. F prime of 4 is 3 times 4 squared, that's just 16, minus 12 times 4 plus 9. So this is 48 minus 12 times 4 is just 48, and then plus 9. These 48s will cancel, we just get 9. So this means that our first derivative is positive for x values greater than 3. Basically, between all your critical points, you want to plug in test values to see the sign of the first derivative. Because your first derivative is positive for x values less than 1, this means your function is increasing for x values between negative infinity and 1. Notice we're not including x equals 1 because the first derivative there is 0. That's where we found our critical point. And if the first derivative is 0, that means the function it kind of levels out instead of being increasing. Now, it also is increasing for x values greater than 3. So that would be 3 to infinity with this union showing we're including both of them. And then decreasing for x values between 1 and 3. Okay, so that's the first part done. Alright, so the second part says to identify all maxima and minima and to find their exact locations. So to do that, we're going to test our critical points to see if they are maximums or minimums. And we're going to do that using the first derivative test. So notice that x equals 1, which is one of our critical points, our function's derivative switches from positive to negative, which means our function switches from increasing to decreasing. So it kind of looks like this. By our first derivative test, that means that this has to be a maximum, a local maximum, where at x equals 3, it switches from negative to positive, meaning that our function switches from decreasing to increasing. So it would look like this. That is a local minimum. So now it says to find their exact locations. So let's get a point. So our maximum occurs at x equals 1. Let's plug in 1 into f. So 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. So this is 1 minus 6 plus 9 plus 2. So that's negative 5 plus 11, which is 6. This means that we have a local maximum at the point 1, 6. And our minimum occurs when x is 3. So if we plug in 3 into our function, we get 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2, which is 27 minus, so 6 times 3 squared, that's 6 times 9. 6 times 9 is 54 plus 9 times 3 is 27 plus 2. 27 plus 27 is just 54. So 54 minus 54 plus 2. These 54s will cancel out and we'll just get 2. So this means that we have a local minimum at the point 3, 2. Alright, let's do one more example and then we'll be done. Alright, for this one, we have y equals 3 sine of 2x minus 10, so a sinusoidal function. And we're asking for x values between 0 and 2 pi. We want to find the intervals of increase and decrease, and then determine the x values of the local minima and maxima. So the first step is just to take a derivative. So our derivative dy dx, we're going to differentiate 3 sine of 2x minus 10. Well, differentiating this constant, we'll just make it go away. And then we'll have 3 out in front, so we can just pull that out of the derivative. And then we need a chain rule. Our outside function is sine of x, and our inside function is 2x. The chain rule says that we need to do the derivative of the outside evaluated at the inside, all times the derivative of the inside. So we'll have 3 times the derivative of sine, it's just cosine, of the inside, so 2x. And then the derivative of 2x is just 2. So we get 6 cosine of 2x. So the derivative of a function dy dx is just 6 cosine of 2x. Now, to find the intervals of increase and decrease, we just need to find where this is equal to 0. So find our critical points. Note, we won't have any critical points that are at a place where the derivative is undefined, because cosine is defined for all values of x. So all of our critical points will happen where our derivative is 0. So let's just set 6 cosine of 2x to 0. We'll get cosine of 2x is 0. Alright, so cosine of 2x equals 0. Where does that happen? Let's look at a unit circle. So the unit circle tells us, based on the x and y coordinates of the points on the circle. Let me draw our circle. Based on the x and y coordinates of the points on the circle, that tells us the cosine sine of our angle. So the cosine is the x-coordinate, which is 0 when we intersect the y-axis. So right there. So this is pi over 2. This is 3 pi over 2. And then we can keep going around the circle. So 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. And we can repeat that. So basically, if we keep going pi around the circle from pi over 2, we're going to keep hitting those zeros of cosine. What this means is that when the argument of cosine is pi over 2 plus some multiple of pi, that means that the cosine is going to be 0. So that means that this argument on the inside, 2x, has to be pi over 2 plus k pi, where k is just some integer. So we have a 2x equals pi over 2 plus k pi. This means x, if we divide both sides by 2, x is pi over 4 plus k over 2 pi. So both of these terms have a pi over 2 we can factor out. So from this first term, if we factor out pi over 2, we'll just have a half. In the second term, we'll just have k. Well, we only want x values between 0 and 2 pi. So let's solve for k values that satisfy that. We want x to be between 0 and 2 pi, meaning we want this expression between 0 and 2 pi. So 0 less than or equal to pi over 2 times 1/2 plus k, which is less than 2 pi. Now, if we multiply both sides by 2 over pi, we'll get, on the left side, we'll just get 0, because 0 times anything is just 0. It is less than or equal to 1/2 plus k, which is less than 2 pi, but when we multiply both sides by 2 over pi, these pi's will cancel out. We'll just get 2 times 2. So this is all just 4. So 0 is less than or equal to 1/2 plus k, which is less than 4. If we subtract 1/2 from both sides, we'll get negative 1/2 is less than or equal to k is less than, so 4 minus a half is just 7/2. And notice k has to be an integer, and we only want integers that satisfy this. So the integers that satisfy us are k equals 0, 1, 2, and 3. If we plug in k equals 4, it's definitely greater than negative 1/2, but it is not less than 7/2. So these are all the integers that will satisfy our equation. Now let's write out what all of these x values will be. Alright, so these are all of our zeros. They're given by pi over 2 times 1/2 plus k. If we plug in k equals 0, we get pi over 2 times 1/2 plus 0, that's just 1/2. So pi over 2 times 1/2, that's just pi over 4. K equals 1. We get pi over 2 times 1/2 plus 1, that's 3/2. So we get 3 pi over 4. K equals 2. We get pi halves times 5 over 2. That's 5 pi over 4. And a similar process goes for k equals 3. You get 7 pi over 4. Alright, so that was all the work to find our critical points for our function. Now, we did that so that we can find our intervals of increase and decrease. So to do that, let's do what I said before, and let's make a number line. This will be pi over 4. This will be 3 pi over 4, 5 pi over 4, 7 pi over 4. Alright, to do this, let's plug in a test point right here. You'll see once we plug in one test point, it'll become really easy to find out the signs of the derivative for the other intervals. So we have pi over 4 and 3 pi over 4. Something between that is 2 pi over 4, but that's the same thing as pi over 2. So let's plug pi over 2 into our derivative. 6 cosine of 2 times pi over 2. That's 6 cosine of pi. Cosine of pi is just negative 1, so this is negative 6. So this is negative, meaning that our function is decreasing for x values between pi over 4 and 3 pi over 4. Well, if you think of a sinusoidal function, it's going to switch at these zeros. So it's going to do something like this, where at each of these critical points, it's going to be switching sign, meaning that we can just kind of go along these intervals and find out the signs. So this will be negative, this will be positive, negative, positive. It kind of just alternates. Now, this has to be for x values between 0 and 2 pi. So you can think we start out here at 0, and then we end over here at 2 pi. Now, where the derivative is positive is where the function is increasing, and where the derivative is negative is where the function is decreasing. So, our increasing intervals, we know that from 0 to pi over 4, from 3 pi over 4 to 5 pi over 4, and from 7 pi over 4 to 2 pi. Actually, we can use closed brackets for these endpoints because if you notice, all of these intervals have length pi over 2, but these ones at the end just have length pi over 4. So it's actually going to be positive. The first derivative is going to be positive for x values in this whole interval of length pi over 2. But this interval right here, from 0 to pi over 4 with length pi over 4, it's going to be positive in the entire interval, including at the endpoint of 0. So that can be a closed endpoint. Meanwhile, for 2 pi, actually, it has to be an open endpoint because we're only thinking about from 0 to 2 pi, where the endpoint at 2 pi is open. Now, similarly, to find where the function is decreasing, we find where our first derivative is negative. That happens from pi over 4 to 3 pi over 4, and from 5 pi over 4 to 7 pi over 4. Okay, so those are our intervals of increase and decrease. Our minima occur where our first derivative switches from negative to positive. So our minima occur at x equals 3 pi over 4, and at x equals 7 pi over 4. For part B, our function will have maxima where our first derivative switches from positive to negative. That happens at x equals pi over 4 and x equals 5 pi over 4. So these points. Alright, thank you for watching. In the next video, I'm going to start talking about the second derivative, so like the second derivative test and concavity and inflection points and all that. Anyways, I hope that you found the video helpful, and have a good rest of your day.